Hey everyone, welcome back to 197 Concepts. In this video, I'm going to tell you how to generate a 75 milliseconds of time delay using timer in mode 2. Okay, so before going there, you have to clearly understand a basic concept. Let me just clear this page. So for the timer, you will be having four modes, or you can say that you can operate a timer in four different modes. That is mode 0, mode 1, mode 2, and mode 3. So mode 0 is 13-bit mode. Okay. Mode 1 is 16-bit mode. Mode 2 is 8-bit auto reload mode. Auto reload. And M3 mode 3 is 8-bit split mode. Okay, so you are specifically focusing on this M2, that is mode 2. So 13-bit, so you will be having 13 bits. You will be counting from 0 to 8192. Sorry, 8191. It's 2 power 13 up to that value, and then you're going to stop. In M1, that is mode 1, you will be counting from 0 to 65,535, and then you're going to stop. In mode 3, you will be splitting. So 2 power 8 will give you 2 power 256 value. So even in M3 mode, you will be counting from 0 to 255, and then you're going to stop the timer. Whereas in M2, what you are going to do is you're going to count from 0 to 255. But instead of stopping here, again you're going to load the timer value with the 0, and again it's going to count from 0 to 255. After completion of this, it's going to again load it for 0 value. Then again it's going to count from 0 to 255. Again it's going to load. So that's a cyclic process. That's the difference between the mode 2 and all the other different modes. But here there's a catch, because M2 in mode 2, you're having only 8 bits, and the maximum value that you will be counting is 255 if you count 0 also, or else 256. This value is nowhere possible to generate a time delay of 75 milliseconds. Okay, so at a maximum, this can create a delay of 250 microseconds itself. It's not possible to generate a time delay of 75 milliseconds using this mode. Okay, this is possible. So 75 milliseconds is possible by using mode 0 or mode 1. There's no doubt in that. But by using mode 2, that's the thing. That's the thing you have to observe here. So my idea here is, first of all, I'm going to generate a 250 microsecond time delay. But this is going to be multiplied into 300 times. Okay, so 250 multiplied by 300, this will give me, I'm going to split this 25 into 3, a 10 is remaining there and 100 is remaining there. Okay, so 25 times 3 will give you 75. Okay, and this is 1000. Okay. Oh, sorry, my bad. I've observed this. I forgot this micro. So let's redo this calculation. Yeah, that's what I was thinking. I have missed here something. Okay, so yeah, from here. So 250 micro into 10 to the power of minus 6 into 300. Okay, so keep this 10 to the power of minus 6 as it is. So 25 into 3, the remaining is 10 from 250 and 100 from 300. And as I'm having 10 to the power of minus 6, so 25 times 3 will give you 75, and this is 1000 into 10 to the power of minus 6. So 75 as it is. 10 to the power of say cube into 10 to the power of 3 into 10 to the power of minus 6. Okay, so let me raise this a little bit. This is not visible here. I need the pen. So 10 to the power of minus 6. Since the bases are same, what we can do is 75 into 10 to the power of 3 minus 6, which is nothing but 75 into 10 to the power of minus 3. So that 75 into 10 to the power of minus 3 will become milli. And since I'm talking here with seconds, so that will give you a 75 millisecond time delay. Okay. So again, I'm going through my idea. So in mode 2, I'm going to count from 0 to 255. That's a total count of 256. Okay. So if you remove this value, yeah, if not remove this value, I'm using this mode 2. I'm using this mode 2 to generate a time delay of 250 microseconds, and this will be multiplied by 300. So instead of uh, repeating this time delay generation for 300 times, what I'm going to do is I'm going to first of all generate a 250 microsecond time delay. Then I'm going to take loop 1 for 3 times. Okay, 3 times. Then within this loop 1, I'm going to add another loop for 100 times. Okay, so overall, so loop 2 first of all will be executed for 100 times, but the loop 1, this is named as outer and this is named as inner. Okay, so inner loop will be executed for 100 times first, and it will be updated. It will be reduced as 2. Then again, it will be then the loop 2 will be again executed for 100 times, and then this will be reduced to 1 again for 100 times. Overall, this will be executed for 300 times. Okay, so that's my idea. And if you observe the program that I have pasted here, see you are using timer 0. You're using timer 0 in mode 2. That's why I'm initializing tmod with 02h. If you search this tmod on the internet and if you split this one, and and if you split this 0 to like 00000010, you will these two bits. So if you search the values, if you search the register of tmod, you will get 8 different bits. And if you split 0 to that, you will be getting 00000010. That 10 will tell us that you are going to initialize a particular timer in mode 2, which is 8-bit auto reload. Now, you might have observed here, I'm loading the lower bit of lower 8 bits of timer 0 with 06h. Okay, so in order to generate a 250 microsecond delay, what is my total count? That's 256. So if I need to generate a delay of 250 microseconds, I need to remove this only 6. That's why I'm going to go for 250. And yeah, if I already have a 6 value, then I have to go only 250 steps further, which will generate a 250 microsecond time delay. Okay, 250 microsecond time delay. That's why I'm loading the th0 value with 06. Again, I'm going to push the value into port 1 with the 00h. Then I'm going to move this value from P1 to A in order to complement it. And then again, I'm going to move it into P1. So in order to get a clock pulse like this. Then I'm going to move here. So this is the I'm going to come here, that is delay 75 milliseconds. Here what I have told you, the outer loop and the inner loop. See, this outer loop will be initiated 3 times, will be executed 3 times, and within that it's going to execute the outer label for 100 times. So R1 and R0. And here I'm going to initialize this. So start the timer. Then the magic is at this line. So this JNB is JNB is jump if bit is not set. So if bit is equals to 0, then so yeah, TF 0. If TF 0 is equals to 0, you have to jump towards the wait label. And if TF 1 is equals to, sorry, TF 0 is equals to 1, there is no need to jump. That's what this line means. So that tells the timer has completed its count. So TF0, when TF0 equals to 1, that tells that timer has completed its count and there is no more space for further counting. That's why after completion of that, there should be no jump. You have to clear the TF0, and uh, if we are not having these two loops, the R1 and R0, outer and inner loop, then we would have stopped the timer. Since we are having the outer loops also, as we need 75 millisecond time delay, what we are going to do is DJNZ. So do not jump, not it's not do not jump, it's decrement and jump when not 0. So DJNZ R0 comma wait, this will tell that decrement and jump when not 0. That is, it is going to check R0 value. So it is 3. This will be decremented to 0. So R0, sorry, it's not 3. By program, we have taken it as 100. We have taken this as 100. So this will be decremented to 99. Since this is not equals to 0, it's going to jump towards the wait. So again, the TF0 will be checked and it will be executing 100 times. Okay, and when we complete this, then we have R1. So DJNZ, so R1 comma outer. So this means decrement jump not 0. So R1 is initialized with 3. This will be decremented to 2 and it will be jumped towards the outer variable. And after completing of all this, we are going to just clear the trap line. If the R1 equals to 0, okay, after completing from 3 to 1 and then it comes to 0, uh, it's not going to jump, because jump if not 0, now this R1 is equals to 0, so not 0 condition is not met, so it is not going to jump. It will be executing, it will go on and further execute this line, that is clear TR0, then it's return and end. So return will go back to SJMP loop. So here, yeah, it's going to come here, and then from the next line, it's SJMP loop. So it will go again here, complement P1, move that to port 1, and again you're going to call this 75 millisecond. Again, you're going to initialize 3. Again, you're going to initialize R0 with 100, and then again you're going to do the wait period. Okay, so that's the explanation of the program. Now, if you run this, I've already typed it. Just go for debug, start stop debug session, click on OK. So you will not get the logic analyzer by default. It will be closed. You have to select here. Okay. So since I have already having that logic analyzer, it is disabled. Now when you click this again and you move out this better view. Okay. You run the simulation. You stop it. Press on Shift. Move towards the edge. Mark. Click it there once to mark it, and then move on towards the next. Now, if you observe the label below at the bottom of the screen, if you observe here, if you observe here at the bottom of the screen, what you are going to see is small d is 74.794 milliseconds. That's approximately 75 milliseconds. Okay, definitely there will be some small differences. You can round up that to 75 milliseconds. So that's it in this program. That's the way you see the output. That's the explanation of the program, and I hope you have understood it. Like how to generate a 75 milliseconds of time delay using timer. If you need to generate 75 milliseconds of time delay using counter, you have to use you have to initialize tmod with some other value. Okay, since I have not used here timer, I have not used here counter, I have used the timer because both the functionalities are same, but For counter, you will get an update of the machine cycle outside from the outside of 8051 using the pins T0 and T1. Now, in a virtual setup, I won't be able to update the 8051 timers by using T0 and T1. That's why I have moved to timer. Okay, so it's the same thing, it's the same program, only Tmod initialization will be different. Other than that, there is no difference. Thank you.